All right, this is the last page of the second review, and I had started it by my phone, got a little sassy here. So what you're wanting to do is to take, when you see f of x plus delta x, you want to put x plus delta x in for x here and here. And when you do that, you create this first part here, 5 times x plus delta x squared minus 2 times x plus delta x. We'll work with that a little bit. Then it says minus f of x, so I went minus, and f of x is this, so then I just put that in for f of x, okay? Over delta x, and we're taking the limit as that. Now this means very little to you right now. Next chapter we'll talk about what this actually defines and helps us with, but for right now it's kind of nonsense, right? So we're not going to worry too much about it. I do want to show you though what happens if we expand this out. We get x squared plus 2x delta x plus x delta x squared. I distribute 5 to that. I get this plus this plus this. And then if I distribute the negative 2, I get that and that. If I distribute the negative, I get this and this. Then what happens is this cancels with that. This cancels with that. And so what we're going to have is 10x delta x plus 5 delta x squared minus 2 delta x over delta x as delta x goes to 0. Now, there is a delta x in all of this, right? So we can pull that delta x out and let it cancel with this. So this delta x will cancel a delta x in each of those. It'll give us 10x plus 5, and then they'll still have a delta x left over, minus 2. Okay? And what we're going to do now is let the delta x go to 0. So when this goes to 0, this drops out, and what's left is 10x minus 2. And that's our answer. Okay. Now, next chapter, what we're going to do is show you that all you have to do is take this exponent times this, subtract 1 from the exponent, so it goes down to 1, and then 1 times 2 is negative 2, and then this goes away, and it's the same answer. We're going to show you a much, much easier way to do this, but it'll be important for you to know what this is representing and why it represents that. We'll get to that next chapter. Okay. All right, our last one here says, can we create a function with a removable discontinuity at 3, non-removable at negative 4, zeros at 1 and 7, and then somehow make f of 0 equal to 14. So let's start with the first one. A removable discontinuity. That means there's a hole in the graph. That means that we had an x minus 3 and an x minus 3 on the top and bottom. Cancels out, creates that removable or that hole. A non-removable is more of an asymptote, right? So that means we have an x plus 4 that would be on the bottom. Okay. Zeros are what makes the function equal 0. Those are going to be up on top. So I'm going to have an x minus 1 and an x minus 7 up there. All right, so this is a good framework for our problem, but now we had one extra thing thrown in just for fun, and that is if we put 0 in for x, we're supposed to get 14 as an answer. So I'm gonna say let's have this all multiply some value a. Don't know what a is, we're gonna see. Some kind of adjustment that we need to make here. And if I put 0 in for x, I'm gonna get negative 3 times negative 1 times negative 7. That's a negative 21 over negative 3 times 4, that's a negative 12. Okay? And when I put 0 in, I want the function to equal 14. So I want this to be 14 over here. Okay? So just to kind of, because I don't have a calculator, the negatives would cancel. I can divide those by 3. And now if I multiply both sides by 4/7, I end up with a equal to 8. Okay, so if a is 8, then that will create this scenario here. So here's my final function then. F of x equals 8 times x minus 3 times x minus 1 times x minus 7 all over x minus 3 x plus 4. And again, all the pieces are there. The removable is at 3, the non-removable at negative 4, the zeros at 1 and 7. And if I put 0 in for x and let this all multiply, 8 will be my answer.